Have you ever wondered why we might be trapped? Not by walls or barriers, but by distance itself. The Milky Way, our home galaxy, spans 100,000 light years from edge to edge. It contains 200 to 400 billion stars, countless planets, nebulae swirling with the dust of creation. It's vast beyond human comprehension. And yet, it's a prison. Because even if we could travel at the speed of light, even with perfect technology and unlimited resources, we would still be confined here. The distances between galaxies are so immense that they transform our cosmic home into an inescapable cage, not locked by any force, but sealed by geometry and time itself. Tonight, as you drift towards sleep, we're going to explore this beautiful prison. We'll trace the boundaries of our confinement, measure the distances we cannot cross, and understand why the Milky Way may be the only galaxy humanity will ever truly know. We'll journey from the edge of our galaxy to the void beyond, from the limits of light speed to the deeper limits of time and human lifespan. This isn't a story of giving up. It's a story of understanding our place in a cosmos so vast that even infinity has boundaries. Before we begin, if you're kind enough, a gentle like or a quiet tap on subscribe would mean the world to me. It's a small gesture, but it keeps these quiet explorations alive and reminds me that these cosmic lullabies still find their way to gentle hearts like yours. Now, let's begin with the first question. Part 1. How far is next door in space? When we look up at the night sky and see the fuzzy patch of light called the Andromeda Galaxy, we're looking at our nearest large galactic neighbor. It's often described as nearby in cosmic terms. Astronomers call it part of our local group, a collection of galaxies bound together by gravity. But nearby is a relative term. Andromeda sits 2.5 million light years away. That distance is almost impossible to comprehend. A light year is the distance light travels in 1 year, moving at 186,000 miles per second. That's about 6 trillion miles. Andromeda is 2.5 million of those light years away. In miles, that's approximately 15 quintillion miles. That's a 15 followed by 18 zeros. According to NASA's measurements, if you could travel at the speed of light, it would take 2.5 million years to reach Andromeda. Not 2.5 million years of your time, but 2.5 million years of external time. You, aboard a light-speed spacecraft, would experience time dilation. From your perspective, depending on how close to light speed you're traveling, the journey might feel shorter. But for everyone you left behind, for Earth and civilization, and all of human history, 2.5 million years would pass. Think about what that means. Humans have existed as a species for roughly 300,000 years. Civilization has existed for about 10,000 years. A journey to Andromeda at light speed would take 250 times longer than all of recorded human history. When you left Earth, humans would be using whatever technology we have now. When you arrived at Andromeda, if humanity still existed, they would be as different from us as we are from early Homo sapiens. They might not even be biological anymore. They might be something we can't imagine. Or they might be gone entirely, extinct, or evolved into something unrecognizable. The European Space Agency notes that Andromeda is actually moving toward us. In about 4.5 billion years, it will collide with the Milky Way, and the two galaxies will merge. But that's a cosmic event, not a solution to our confinement. By the time it happens, our sun will be nearing the end of its life, Earth will likely be uninhabitable, and whatever descendants of humanity exist will have far bigger concerns than interstellar travel. But Andromeda is the closest large galaxy. Most galaxies are much farther away. The Triangulum Galaxy, another member of our local group, is 3 million light years distant. Beyond that, the distances grow rapidly. The nearest galaxy cluster, the Virgo cluster, is 54 million light years away. The nearest supercluster, Laniakea, which contains our local group, spans 520 million light-years. At those distances, even light speed becomes hopelessly slow. A journey to the Virgo cluster would take 54 million years. That's longer than the entire reign of the dinosaurs. It's longer than complex life has existed on Earth. NASA's fastest spacecraft, the Parker Solar Probe, reached speeds of 430,000 miles per hour. That sounds impressive, but it's only 0.064% the speed of light. At that speed, reaching Andromeda would take 3.9 billion years. That's nearly as long as Earth has existed as a planet. Even proposed theoretical propulsion systems don't help much. Nuclear pulse propulsion, which would use nuclear explosions to push a spacecraft, might reach 5 to 10% of light speed. At 10% of light speed, the journey to Andromeda would still take 25 million years. Antimatter rockets, using the annihilation of matter and antimatter to produce thrust, might theoretically reach 50% of light speed. But that still means 5 million years to Andromeda, and the amount of antimatter required would be staggering. According to calculations, you'd need thousands of tons of antimatter, and we currently produce antimatter in quantities measured in nanograms. There are more exotic proposals: light sails pushed by powerful lasers, fusion ramjets that collect interstellar hydrogen as fuel, even hypothetical warp drives that bend space-time itself. But all of these are purely theoretical, and most require technology and energy sources we don't have and may never develop. And even if we could reach light speed, even if we solved every technical challenge, we face a deeper problem: time. Not just the time the journey takes, but the time it takes for information to travel, for communication to cross the void, for any connection to be maintained between the travelers and home. At light speed, a message from Andromeda would take 2.5 million years to reach Earth. If the travelers encountered a problem and sent a distress signal, it would arrive long after any civilization that sent them had risen and fallen. There would be no rescue, no support, no communication in any meaningful sense. The travelers would be alone, cut off from their origin, adrift in a galaxy that would be utterly alien to them. The astronomer Carl Sagan once described Earth as a pale blue dot to emphasize our insignificance in the cosmos. But perhaps the more unsettling truth is that Earth, and the Milky Way that contains it, is an island, isolated by distances so vast that even light, the fastest thing in existence, takes millions of years to cross them. Take a slow breath. Right now, the Andromeda Galaxy is 2.5 million light-years away. The light you see from it tonight left its stars before humans existed, before our ancestors walked upright, before our lineage had even split from other primates. You are seeing ancient light from a galaxy that is, for all practical purposes, unreachable. The universe may be infinite, but the universe we can access is not. It's bounded by speed, by time, by the simple geometry of distance. And those boundaries are far smaller than you might think. But distance is only part of the problem. There's something else that seals our confinement, something more fundamental than miles or light years. That's where we turn next. Part 2. Why is the speed limit absolute? In science fiction, characters routinely travel faster than light. They engage warp drives, jump through hyperspace, or fold space to cross vast distances in moments. It's such a common trope that we've come to expect it. Surely, we think, advanced technology will find a way around the speed limit. Surely light speed is just a barrier waiting to be broken. But physics says otherwise. And not just current physics, fundamental physics, the kind that's been tested thousands of times and has never been wrong. According to Einstein's theory of special relativity, nothing with mass can reach the speed of light. Not almost reach it, not reach it with enough energy, simply cannot reach it. Ever. NASA's particle accelerators have verified this countless times. When we accelerate particles to higher and higher speeds, something strange happens. As they approach light speed, They get harder and harder to accelerate, not because the accelerator is weak, but because the particles themselves become more massive. According to relativity, mass increases with velocity. At everyday speeds, this effect is negligible. But as you approach light speed, your mass approaches infinity. To accelerate something with infinite mass would require infinite energy, which is impossible. The universe simply won't allow it. This isn't a technological limitation. It's not something we can engineer around with better engines or more powerful fuel. It's a fundamental feature of space-time itself. The speed of light is woven into the structure of reality. The European Space Agency's studies of cosmic rays provide more evidence. Cosmic rays are high-energy particles from space, some traveling at 99.99999% the speed of light. These are the fastest natural objects we know of. And even they, with energies far beyond anything we can produce artificially, cannot reach light speed. They asymptotically approach it, but never quite get there. So if we can't reach light speed, what's the realistic maximum? Current estimates suggest that with advanced propulsion systems, we might eventually achieve 10 to 20% of light speed. That's still incredibly fast, about 37,000 miles per second. But at that speed, a journey to Andromeda would take 12 to 25 million years, even if we could reach 90% of light speed, which would require technology far beyond current understanding. The journey would still take 2.8 million years, and the energy required would be astronomical. According to calculations by NASA's Advanced Propulsion Physics Laboratory, accelerating a spacecraft to 10% of light speed would require energy equivalent to all the electrical power generated on Earth for several years. For 90% of light speed, you'd need energy comparable to the total output of a star. We're not talking about a lot of rocket fuel. We're talking about harnessing the power of a sun. But there's another problem with high-speed travel: time dilation. According to relativity, time passes differently for objects moving at high speeds. The faster you go, the slower your time passes relative to the outside world. At 90% of light speed, time dilation becomes significant. For every year that passes on your spacecraft, about 2.3 years pass in the outside world. This might seem like an advantage. If you're traveling to Andromeda at 90% light speed, you would experience the journey as taking only about 1.1 million years of subjective time instead of 2.5 million. Still impossibly long, but shorter than the external time. But this creates a profound disconnect. If you somehow survived the journey, if you used generation ships or suspended animation or some other method to preserve human life across millions of years, when you arrived at Andromeda, the Milky Way you left behind would be millions of years older. Everyone you knew would be dead. The civilization that sent you would be gone. Even the species might be extinct or evolved beyond recognition. You would be a time traveler, arriving in a future you cannot predict and cannot return to, because the journey back would take just as long. And by the time you returned to the Milky Way, even more time would have passed. You'd arrive home to find a galaxy millions of years older than when you left. This is the ultimate isolation. Not just distance, but time. The speed limit ensures that any journey between galaxies is also a journey into the deep future. You cannot go to another galaxy and return to the world you knew. That world will be gone, lost to time, replaced by something unknowable. The astrophysicist Brian Greene describes this as the cosmic speed limit, and it's not arbitrary. It emerges from the structure of space-time itself. Space and time are not separate things. They're interwoven into a single four-dimensional fabric. The speed of light is the speed at which cause and effect propagate through this fabric. If you could exceed light speed, you could theoretically arrive at a destination before you left. You could, in principle, violate causality, creating paradoxes where effects precede causes. The universe doesn't allow this. Causality is fundamental. Causes must precede effects, and that requirement sets the speed limit. Some physicists have proposed workarounds, warp drives that bend space rather than moving through it, wormholes that create shortcuts through space-time. These solutions don't technically violate the speed limit because you're not moving through space faster than light. You're manipulating space itself. But these proposals require exotic matter with negative energy density, something that's never been observed in nature and may not exist at all. Even if it does exist, controlling it in the quantities needed to create a warp drive or wormhole would require technology so advanced it might as well be magic. NASA's Harold White has worked on theoretical warp drive designs, trying to reduce the energy requirements from star level to something more manageable. His calculations suggest that with the right configuration, you might only need the mass energy equivalent of Jupiter. That's still impossible with current technology, but at least it's not a star. Yet even if we solved all the technical challenges, even if we found a way to create stable wormholes or functional warp drives, we'd still face limitations. Wormholes would need to be created between 2 points, meaning you'd have to travel to the destination conventionally first to set up the other end. And warp drives, if they work at all, might still be limited in speed by factors we don't yet understand. The truth is, we're trapped by the structure of space-time itself. The speed limit isn't a suggestion or a challenge to be overcome. It's a fundamental feature of reality, as unchangeable as the number of dimensions in space or the charge of an electron. Take a slow breath. The universe has a speed limit, and that limit seals us in. No matter how advanced our technology becomes, no matter how desperate our need to explore, we cannot exceed the speed of light. And at that speed, the distances between galaxies are so vast that they might as well be infinite. We are confined not by lack of ambition or insufficient technology, but by the laws of physics themselves. The Milky Way is our home, and it may be our only home forever. But even within these constraints, couldn't we find a way? Couldn't we use generation ships or suspended animation or some other method to bridge the vast timescales? That question leads us to another barrier, one perhaps even more insurmountable than distance and speed. Part 3. Why can't we wait long enough? Let's imagine we've solved the propulsion problem. We've built a spacecraft that can reach 10% of light speed. That's fast enough to reach Andromeda in 25 million years. Now, we just need a way for humans to survive that journey. How hard could it be? Impossibly hard. Because 25 million years is not a span of time that has any meaning in human terms. It's longer than humans have existed. It's longer than most mammal species survive. It's longer than continents remain in the same position. It's a geological epoch, not a journey. According to NASA's studies of long-duration spaceflight, humans face severe challenges even on trips lasting months or years. Muscle atrophy in zero gravity, bone density loss, radiation exposure, psychological stress. These problems compound over time, and we've only studied missions lasting up to about a year. The European Space Agency's research shows that maintaining a healthy human population in space for even a few generations would be extraordinarily difficult. You'd need a closed-loop life support system that recycles air, water, and waste with near-perfect efficiency for thousands of years. Any small loss or inefficiency would compound over time, eventually depleting essential resources. You'd need to maintain genetic diversity to prevent inbreeding. That means a population of at least several hundred people, possibly thousands. And you'd need to ensure they remain healthy, reproduce successfully, and don't develop mutations that could harm future generations. But the real challenge is time itself. 25 million years is 1 million human generations. If we assume an average generation time of 25 years, that's 1 million successive generations living, reproducing, and dying aboard a spacecraft. Each generation would be born in space, live their entire lives there, and die without ever reaching the destination. For most of history, the spacecraft's destination would be mythical, a story told by ancestors, a distant promise that might as well be heaven. How do you maintain purpose and cohesion across that timescale? How do you prevent social collapse, rebellion, or the simple drift of culture and goals over millennia? And that assumes the technology remains functional. According to engineering studies, even the most durable materials degrade over time. Metal fatigues, electronics fail, systems break down. You'd need not just redundancy, but the ability to manufacture and repair everything on board for millions of years. That means the spacecraft would need to be a fully self-sustaining civilization. It would need factories, mines for asteroid resources, farms, schools, governments. It would need to be less a ship and more a mobile planet, carrying an entire society through the void. The science fiction concept of generation ships captures this idea. Multi-generational vessels where successive generations live and die during the voyage, with only the final generation reaching the destination. But most generation ship scenarios envision journeys of decades or centuries, not millions of years. At the million-year scale, generation ships become absurd. The culture aboard would drift so far from the original that the descendants might not even remember why they're traveling or care about reaching the destination. They might forget they're on a ship at all, developing myths about their enclosed world that bear no relation to the truth. And consider the technological drift. If the ship left Earth today with current technology and traveled for 25 million years, by the time it arrived, the technology that built it would be 25 million years obsolete. Any messages from home would describe a civilization completely unrecognizable to the travelers. In fact, messages from home would become increasingly rare and then stop entirely, because Earth wouldn't remain a stable transmission source for millions of years. Civilizations rise and fall. Species go extinct. Planets change. Within a few million years, Earth might be unrecognizable or even uninhabitable. The transmission sources would go silent, and the travelers would be truly alone. Some have proposed suspended animation or cryogenic freezing as a solution. Put the crew in a state of suspended metabolism. Keep them frozen for the duration of the journey and wake them when they arrive. This solves the generational problem, but creates others. According to current medical science, we can't freeze and revive humans without damage. Ice crystals form in cells, destroying tissue. Even if we solve that problem with cryoprotective chemicals, there's no guarantee that metabolic processes can be suspended for millions of years and then restarted. And even if the crew survives in suspension, someone or something needs to maintain the ship, either automated systems, which would need to function flawlessly for millions of years, or a rotating crew, which brings back the generational problem. Another proposal is mind uploading. Transfer human consciousness into digital form. Run it as software during the journey, and either remain digital at the destination or build new biological bodies. This is entirely theoretical and raises profound philosophical questions about identity and continuity. But even if it worked, you'd still need hardware that functions for millions of years, and you'd arrive at a destination that's completely alien to the culture and context you left behind. Perhaps the most honest assessment comes from physicist Paul Davies, who notes that interstellar travel at these timescales is effectively one-way and terminal. The travelers, whether biological or digital, would be severing all ties with their origin. They would arrive at the destination as foreigners, strangers to everything that came before, starting from scratch in a galaxy that knows nothing of them. And that's assuming they survived the journey. The interstellar medium is not empty. It contains dust, gas, and occasional larger particles. At high speeds, even tiny particles become deadly projectiles. A grain of sand hitting a spacecraft traveling at 10% light speed would impact with the energy of a large bomb. NASA's studies of interstellar travel identify this as one of the major unsolved problems. Any high-speed spacecraft would need massive shielding, adding weight and reducing acceleration. Or it would need to navigate through the thinnest regions of space, adding distance and time to the journey. And there's radiation. Cosmic rays, high energy particles from distant sources, constantly bombard anything in space. Over millions of years, this radiation would damage electronics, degrade materials, and potentially harm any biological organisms, even in suspended animation. The spacecraft would need to be built like a fortress, heavily shielded, massively redundant, with systems that can repair and replace themselves indefinitely. It would need to be, in effect, a self-sustaining ecosystem that can function without external input for geological timespans. No human institution has lasted 1,000,000 years. No human structure has remained functional for even 10,000 years without maintenance. The pyramids are eroding. Ancient stone monuments are crumbling. Even geological formations change over millennia. Asking a spacecraft to function for 25 million years is asking it to outlast entire species, to survive longer than most lineages on Earth have existed. It's not engineering, it's fantasy. Take a slow breath. Time is our enemy. Not the time of the journey, though, that's enormous, but the time required for maintenance, for survival, for continuity. We are creatures of decades, not epochs. Our technology lasts years or centuries, not millions of years. Our civilizations rise and fall in mere millennia. To reach another galaxy, we would need to transcend time itself. To build something so enduring, it outlasts mountains, so stable, it survives the rise and fall of continents. We would need to be something other than human, something that operates on geological or cosmic timescales. But we are human, and humans, for all our ambition and ingenuity, are temporary. Our lives are brief. Our structures decay. And 25 million years is an eternity we cannot endure. Yet, even if we could overcome time, even if we found a way to preserve ourselves or our descendants across the eons, there's one final barrier, one that has nothing to do with technology or biology, but with the universe itself. And it's the most absolute confinement of all. Part 4. Why is the universe itself working against us? We've talked about distance, speed, and time. But there's a fourth barrier to leaving our galaxy, one that's even more fundamental. The universe is expanding, and that expansion is accelerating. According to measurements from NASA's Hubble Space Telescope and the European Space Agency's Planck satellite, every galaxy beyond our local group is moving away from us. This isn't because they're traveling through space. It's because space itself is expanding, carrying them along. The expansion is described by the Hubble constant, currently measured at about 67 to 73 kilometers per second per megaparsec. That means for every 3.26 million light-years of distance, space is expanding by about 67 to 73 kilometers per second. The farther away something is, the faster it's receding. For nearby galaxies like Andromeda, this expansion is negligible. Andromeda is actually moving toward us because the gravitational attraction between it and the Milky Way is stronger than the expansion of space at that distance. In about 4.5 billion years, we'll collide and merge. But beyond our local group, expansion dominates. Galaxies in the Virgo cluster, 54 million light-years away, are receding at about 100 kilometers per second. More distant galaxies recede even faster. And this recession is accelerating, driven by a mysterious force called dark energy. Dark energy makes up about 68% of the universe's total energy content. We don't know what it is or why it exists, but we know what it does. It pushes space apart, causing the universe to expand faster and faster over time. This acceleration has profound implications for intergalactic travel. Not only are distant galaxies already far away, but they're moving farther away every second. And the rate at which they're moving away is increasing. According to cosmological models, there's a distance beyond which galaxies are receding faster than the speed of light. Not because they're moving through space faster than light, But because space between us and them is expanding faster than light can cross it. This boundary is called the cosmic event horizon, currently about 16 billion light-years away. Galaxies beyond this horizon are unreachable. Even if you traveled at the speed of light, you could never catch them because space is expanding faster than you can travel through it. It's like running on a treadmill that's accelerating faster than you can run. No matter how much effort you expend, you'll never reach the end. And this horizon is shrinking, not in terms of physical distance, but in terms of which galaxies are within reach. As the universe continues to expand and accelerate, more and more galaxies cross the event horizon and become unreachable. NASA's calculations show that currently, about 94% of the galaxies in the observable universe are already beyond the event horizon. We can see them because their light started its journey toward us long ago, when they were closer. But we can never reach them. No spacecraft, no matter how fast, can catch up to a galaxy receding faster than light. Even galaxies that are currently reachable won't stay that way forever. According to cosmologist Lawrence Krauss, in about 100 billion years, all galaxies outside our local group will have disappeared from view. Their light will be redshifted so far into the infrared that it becomes undetectable. The observable universe will shrink to just our local group, the merged remnant of the Milky Way and Andromeda, plus a few smaller satellite galaxies. Future observers in that distant era, if any exist, will look up at an empty sky. They'll see no evidence of the Big Bang, no distant galaxies, no cosmic microwave background. They might conclude they live in a small, static universe, completely unaware that billions of galaxies once existed beyond their horizon. This means we live in a privileged time, a brief cosmic window when intergalactic space is still visible, when the evidence of the universe's origin and evolution hasn't yet faded into darkness. But that window is closing, and the rate of closing is accelerating. For human timescales, this doesn't matter. The changes happen over billions of years. But for any long-term plans to explore the cosmos, it's a hard deadline. Eventually, there will be nothing beyond our local group to explore. The rest of the universe will have slipped beyond reach, carried away by the expansion of space. But even within the time we have, the expansion creates insurmountable problems for intergalactic travel. Consider a journey to a galaxy currently 100 million light-years away. If you traveled at 50% light speed, you might think the journey would take 200 million years. But during those 200 million years, space is expanding, carrying the destination galaxy farther away. By the time you reach where it was, it's no longer there. It's moved farther away. You're chasing a receding target, and depending on how fast it's receding, you might never catch it. The European Space Agency's studies of cosmic expansion show that for distances beyond a certain threshold, even light-speed travel isn't enough. The destination recedes faster than you can approach it. You could travel forever and never arrive. This is the ultimate prison. Not walls or barriers, but geometry. The structure of space-time itself conspires to keep us confined. Distances are vast, speeds are limited, time is finite, and space itself is expanding against us. We are trapped not by lack of technology or insufficient understanding, but by the fundamental laws that govern the universe. No matter how advanced we become, no matter how desperately we wish to explore, we cannot escape these constraints. The Milky Way is our home, and with very few exceptions, primarily nearby galaxies that will eventually merge with us, it's the only home we'll ever have. Take a slow breath. The universe is infinite, but the universe we can access is not. It's bounded by light speed, by expansion, by time itself, and those boundaries are shrinking, closing in, making the accessible cosmos smaller with each passing moment. We are cosmically alone, isolated on an island of stars in an ocean of expanding space. And that ocean is growing, pushing other islands farther away, until eventually we'll be surrounded only by darkness. unable to see or reach anything beyond our local shores. But before we fully accept this confinement, there's one more question worth asking. Even if we can't leave physically, couldn't we send something? A message? A probe? A piece of humanity? If we can't go ourselves, couldn't we at least say we were here? That question leads us to our final exploration. What could we send into the cosmic void? Part 5. Why even our messages won't reach anyone. If we can't travel to other galaxies, perhaps we can send messages, radio signals, laser communications, or physical probes. We might not be able to go ourselves, but we could at least announce our existence, share our knowledge, leave a mark on the cosmos beyond our galaxy. But even this, it turns out, is far more difficult than it seems, because sending messages between galaxies faces the same insurmountable challenges as sending ships. Let's start with radio signals. In 1977, NASA launched Voyager 1, carrying a golden record with sounds and images from Earth. It also carried a message, a map showing our location in the galaxy. The idea was that any alien civilization that finds Voyager could use the map to visit us. But Voyager 1, traveling at 38,000 miles per hour, will take 40,000 years to pass near another star system. And it's not even aimed at one, it's just drifting, heading in the general direction of the constellation Ophiuchus. In about 300 years, it will leave the solar system entirely, entering interstellar space proper. At that speed, it would take Voyager 1 about 29 billion years to cross the Milky Way. That's twice the current age of the universe. Long before it crossed our galaxy, let alone reached another one, the spacecraft would be destroyed by collisions with interstellar dust or degraded by radiation. The golden record would be unreadable. The spacecraft itself, a piece of space junk. Radio signals travel faster, at the speed of light. That's 186,000 miles per second, vastly faster than any physical spacecraft. A radio message could reach Andromeda in 2.5 million years instead of trillions. Still slow, but at least conceivable. But radio signals weaken with distance. According to the inverse square law, the strength of a signal decreases proportionally to the square of the distance. Double the distance, and the signal becomes 4 times weaker. Triple the distance, and it's 9 times weaker. By the time a radio signal from Earth reaches Andromeda, it would be unimaginably faint. According to calculations by SETI researchers, detecting such a signal would require a radio telescope larger than anything we've ever built, pointed exactly at the source, listening at exactly the right frequency. And that assumes the signal isn't drowned out by cosmic background noise. Space isn't silent. It's full of natural radio sources, pulsars, quasars, supernovae remnants, active galactic nuclei. These sources produce radio noise that would overwhelm a weak signal from across intergalactic space. To send a detectable message to another galaxy, you'd need a transmitter powerful enough to outshine the radio noise of the entire Milky Way. That would require energy output comparable to a significant fraction of a star's total luminosity, focused into a narrow beam aimed at the target galaxy. NASA's Deep Space Network, the most powerful communication system we have, uses transmitters with power measured in kilowatts. To send a detectable message to Andromeda, you'd need power measured in petawatts or more. That's thousands of times more power than all of human civilization currently generates. And even if you built such a transmitter and aimed it at Andromeda and sent a message, you'd have to wait 2.5 million years for the signal to arrive. Then, if anyone received it and sent a reply, you'd wait another 2.5 million years for the response. That's a 5 million year round-trip communication time. No civilization lasts 5 million years. Humanity has existed for 300,000 years and has had radio technology for barely 100 years. In 5 million years, humans as we know them will likely be extinct or evolved into something unrecognizable. the civilization that sent the message wouldn't exist by the time any reply arrived. What about physical probes? If we can't go ourselves, could we send robotic emissaries? Probes that could cross intergalactic distances and report back what they find. Again, the numbers are daunting. A probe traveling at 10% light speed would take 25 million years to reach Andromeda. That's 25 million years during which it must function flawlessly, navigating through space, avoiding hazards, maintaining power and communication systems. The European Space Agency's Rosetta mission, which rendezvoused with a comet, operated for 12 years. The Voyager probes have lasted about 45 years and are still functioning, though their power is fading and they'll go silent within the next decade. But these are journeys measured in years, not millions of years. A probe designed to function for 25 million years would need to be fundamentally different from anything we've built. It would need self-repair capabilities, redundant systems, and the ability to gather resources from space, mining asteroids or comets for raw materials. It would, in effect, need to be a self-sustaining machine civilization. And even if such a probe reached Andromeda, the data it sent back would take another 2.5 million years to reach us. By the time we received images of Andromeda's stars, they would be 2.5 million years out of date, and the civilization that launched the probe would be long gone. There's another problem, more philosophical than technical. What would be the point? If the message or probe won't arrive for millions of years, and any response won't return for millions more, what are we communicating? What information could possibly remain relevant across such timescales? We might send mathematical constants, physical laws, images of Earth and humanity. But what would that mean to a civilization millions of years in the future, evolved in ways we can't predict? It would be like ancient cave paintings trying to communicate with us. Interesting perhaps, but not meaningful in any practical sense. The SETI Institute, which searches for extraterrestrial intelligence, focuses on detecting signals from within our galaxy. Even there, communication is challenging. A signal from a star 1,000 light years away would take 1,000 years to reach us.